And a fun night of science is on the way. So kick back, relax, while we learn what's new in science today. At the Science Cafe, at the Science Cafe, at the Science Cafe.
Thank you so much for coming to our second back in person post-pandemic COVID situation. We are going to be recording this on Zoom as well, so there will be a little bit in between the virtual world and the real world at the moment. So if we are pulling questions, they're most likely from the chat. So I'm sorry if there are other ones, but we will try to get to everybody. We are going to have usual style of 3 question and answer sessions. So please feel free to raise your hand, ask your question. I most likely will be repeating it just so that the mic can pick it up. And it's not because I don't necessarily understand you, it's just because I need to be able to tell the people at home what you're asking. So once we are started recording, we're good. I'm going to go through and just give us a little information about Life Science Cafe. So welcome everyone. My name is Julia LaValle. I'm a PhD student in the Neuroscience and Behavior program at UMass, and I will be the one doing the emceeing tonight. So to give you a little background on our group, Life Science Cafe was founded in 2011 by Organismic and Evolutionary Biology, and since has moved to an interdepartmental program. We are organized by graduate student researchers at the University of Massachusetts Amherst. Each month, we invite experts to share and discuss their research. We would like to thank our funders, the Organismic and Evolutionary Biology program, the Graduate Student Senate, and the Graduate School at UMass, as well as the National Science Foundation and our generous UMass Gives donors. Feel free to subscribe to our mailing list and stay tuned for future sessions. We do have a sign-up sheet on the front table over there if you want to add yourself to our mailing list. We are also now hosting hybrid events to benefit both our virtual and in-person viewers. In addition, we're trying to make our events more accessible to everyone. This includes having closed captioning for those of us who are hard of hearing and also offering events in other languages so that we can have people who have different first languages and present them in the language they want to talk. Closer?
Can you speak more? A little bit more?
Speak more? That sound better?
Yeah, it's
Awesome.
Make sure you can hear it coming on there. That way we get it up.
Sounds good. If there is anything you would feel would improve accessibility in our events, please feel free to let us know, either by emailing us or just talking to one of us. We're always happy to listen. All right, so to start us off on our actual cafe, I'm going to introduce Dr. Mandy Mueller here today to talk to us. She is a professor with a research lab here at UMass Amherst, currently in the Department of Microbiology. Originally did get training in France, where she got her bachelor's, master's in biology and biosciences. And she got her PhD at the Pasteur Institute in Paris, France, in virology. She did a postdoc over here in UC Berkeley, which is how I believe she ended up in the States. And she is currently with us at UMass studying viruses, and a particular focus on the herpesviruses. Thank you very much for joining us today, Dr. Mueller.
Thanks for having me, and surprised tonight is in French.
Sad, no. I did learn French for 12 years though, so I'm not good at it. So I'm sorry. Can't do a surprise one. So with our first couple questions, there are some things I want to get established right off the bat, because I know this can be a little bit of a difficult subject sometimes. So you study viruses, but what exactly defines a virus? What is in that category? Are they like alive creatures, or are they just kind of something that's doing their own thing, even if there isn't any life in them?
So that's usually a question. Oh, I can hear myself. We're good. So this is typically a question that everyone asks, whether viruses are alive or not, because this is a difficult concept. And so I always give different answers, but the one that usually sticks in people's mind is that I view viruses kind of like seeds. So if they're out there, they're not doing anything, but they're not really dead either. So you have to plant them in the soil for them to grow into a beautiful plant or a beautiful flower. And so I view viruses the same way. So there are these tiny organisms that have huge potentials, but until you plant them into something, they won't do anything. And so unless they find the proper host, unless they find the proper cell, they won't do anything. So they're not really dead, but they're not really alive either. So they are kind of in between.
Awesome. So one of the things they often get compared to a lot, I feel like, in any sort of class is bacteria. Can you go through like the differences between the two, what considers like bacterial versus viral situations?
Yeah, so people often compare them just because we think of them as microbes, and we think of things that makes us sick, and so we kind of tend to clump them together, the viruses and the bacteria. But in fact, they're really different. So the first thing is the viruses are much smaller, and although things are changing, and we're discovering really huge viruses that tend to be the size of bacteria, so that's kind of fun. But that's a different topic. But in general, those viruses are much smaller than bacteria. And bacteria is something that is kind of self-sufficient, in the same way that we are self-sufficient. So we still need to be fed, and we still need sunlight, and that's true for bacteria as well. But still, if they need resources, they can produce it themselves. Viruses are different in the sense that they can't do anything without their hosts. And so typically the viruses that we study, even though they're kind of big, they can do a lot, but they still cannot produce the basic forms of molecules that they need to survive. So that's a major difference.
Awesome. So one of the big things that you study, and a big part of virology and viruses, is RNA itself. So what is RNA, and why is it important to viruses?
So it's kind of funny because a few years back, most people didn't hear about RNA at all, and the one thing that this pandemic really brought forward is RNA, and RNA vaccines, and RNA this, and RNA that. And so RNA is a really important molecule in our cells. We know of DNA because we know it's the carrier of information. We know our genes are encoded in DNA. And we hear a lot about proteins, because you need to eat your proteins, and these are the sort of the molecules that you need to do things in cells and in people. But there's something in between. There's something between the DNA and the proteins, and that something is RNA. And so RNA is really important for that middle step. And so, it's something that's very flexible, that's something that allows a lot of mutations, a lot of changes, of flexibility, but at the same time is still sort of a template, a backbone for protein expression. So RNA is very important for viruses, but RNA is also very important for us and for all forms of life, basically.
So there's different types of RNA. Is there a particular type of RNA in the virus itself that you study, and that's particularly important for them in particular?
Yeah, so the viruses that we study, they basically have the same biology as us. So their genetic information is carried on DNA, just like us, and they use RNA, just like us, to be able to produce proteins. And so the RNA in particular that we study is called mRNA. So again, this COVID vaccine, the mRNA vaccine, this is the same thing that we're studying, is that molecule that's in between DNA and protein. The other types of RNA are RNAs that are not important for protein per se, and have different roles in cells. And these are not necessarily the RNAs that we study, although they're pretty cool too.
Okay, awesome. So what specifically is your research on? Like, which viruses are we talking about? What are you looking at?
So we study herpes, and so we're very popular, right? So what we study is, these viruses are kind of weird in the world of viruses. If you're infected with a flu virus, for example, you expect it to clear this infection after 2 weeks. You will not have this virus in you after about 2 weeks. For herpes viruses, it's very different. Once you're infected, you really cannot clear this infection. So you will carry this virus with you for a very long time. And so that's very different from other viruses. And so they have to have specific mechanism to allow them to do this, to stick with you for so many years. And so they're little weirdos in the world of viruses, and that's what we love by herpes viruses. And so this is really what we study, trying to understand why is it that they stick with you for so long.
How did you become interested in viruses? And I'm also going to ask you, how did you become interested in herpes virus specifically, not something like catchy right now, like COVID viruses and something like that?
Right. Yeah, so I try to think about this question a lot. Was there a spark moment where it was I want to study viruses? And there's really not an event that I can go back to and thinking, oh, this is it. So what I remember is in high school, we talked about HIV, and my teacher said, we will never have a vaccine against HIV. That's just not how it's going to happen.
Old.
Right? And I was like, but why? Why? And I guess the teacher didn't know the answer. It was just oh, this is the way it is. We will not have a vaccine against HIV. And I was so frustrated. I was like,
worst answer to give a person.
Right, I want to know. I will never know this. I will die one day not knowing this. I was frustrated. And so I guess this is my spark moment, I guess, this frustration. And so I just continued to study biology because you need a lot of biology to study virology. And I eventually ended up working on viruses. Why herpes now? That's a different question. So the first few viruses that I worked on are a specific type of viruses that cause cancer. So they're called oncogenic viruses. And these also are kind of weird viruses, right? We think of cancer as something that's in us. Our cells are messed up in some ways and eventually will lead to cancer. But here we have viruses that by being infected with those viruses, you can develop some type of cancer. This is very weird. Everything that's weird is super interesting to me. And so I studied HPVs, papillomaviruses, but some of those herpes also cause cancer. So that's how I ended up working on those viruses.
Amazing. That's really cool. So how do you actually study a virus? Like if you're doing animal research, it's a little clearer that you're handling the animals, but what does a virus researcher look at?
Right. So it will depend on every virologist that you ask that question to. So for us, our viruses, they're not really dangerous. Everyone has herpes, that's just the way it is. So we don't have a lot of biosafety containment rules that we have to follow. So we have, we work in the lab, obviously we have containment, we have biosafety cabinets and things like this, but we don't go back to our home at night thinking, oh, what if I carry this dangerous virus with me? And so for us, it's really just a question of having in our labs the proper cells that are going to be infected by these viruses, and having viruses in test tubes, and then we put them together different ways and we see what happens. This is really a kid's dream, really. You just have an idea and you test it in your lab, and so this is really a dream job, guys.
I like it. Really manipulatable.
Oh yeah.
Oh yeah. Okay. So that sounds like that's a potential for a lot of different types of viruses, though. So what does the human body do to make sure we're not constantly getting 1,000 viruses that are different recombinations and stuff?
Well, we are exposed to a lot of viruses, and we do get infected a lot. But we have a system in place that protects us and try to fight off these viruses, and that's our immune system. And so there's always a crosstalk between pathogen trying to infect us and our immune system trying to keep them out. And so again, for herpes viruses, this balance is a little bit shifted because the virus sort of wins this fight because the virus is in us and the virus will stay with us until we die. And so really this is the only thing that will kick out this virus is when we die. And so this sort of fight between the host and the virus is very different in herpes viruses. And this is part of why they're also associated with cancer development.
Awesome. So that's a lot of information. Do you want to do a quick little recap of kind of the process of infection? I think you have a slide for this one as well. That might be helpful for people, and I apologize if things are a little washed out. Just nature of the projector, I'm afraid.
Yeah, my slide was beautiful.
It does, I can say, it looks great. Zoom people are having a great time.
All right, so basically what I tried to do in this slide was to sort of depict what a normal viral infection looks like. So you have viruses floating around all around you, and they are looking for a host. So they're looking for an environment where they can multiply and grow. And so for those viruses that we study, we are the host. We are the perfect environment. And so they have to get into us, and then they have to find the proper cell to infect. And so that again is another barrier for them. It's not just getting into us because we breathe them in or because we're in contact with blood or contact with saliva. Even though they can get inside of us, then they have to find the proper cell to infect. That's not easy for them. But when they do, they really hang on, and they're going to start multiplying and stealing all the resources from the cell to multiply and make more viruses. These new viruses, they will go and infect new cells and eventually come out of you and infect new people. And this is really when our immune system kicks in and sort of detects that something is wrong. All those viruses, they should not be around. Our cells should not look like this. There's really something wrong, and that's a big red flag for the immune system, which will activate and actively work against these viruses. And so destroy those viruses, destroy the cells that are infected, so that they can achieve something that's called clearance. So that's when you're no longer infected with these viruses. And carry a memory of this infection so that if you encounter this virus again, you'll be ready to jump at it sooner rather than later so that you never reach to that point of multiplication. So this is a normal virus. This is what they do. The viruses that we study are a little bit different because when they find that cell that they like, they will take a little detour and enter something that's called latency. And so in this latent phase, they will hang on to the cell that they found, but they really won't multiply. They really won't do much for years and years and years. And so for the longest time, you will not even be aware that you're infected with herpes viruses. And that's why you don't have constant symptoms. You only have periodical symptoms. And so in this latent phase, because there's not a lot of multiplication, there's not a lot of viral activity, your immune system has no idea that you're infected. There's no red flag. There's really no clue that you're infected. And so the immune system is not doing anything. And so that's how you establish lifelong infection. And because those viruses are around and they're in your cells for so long, even though they don't do much, they do a little bit every time your cell divide. And this is really when you can have a virus that triggers cancer. It's because it's been around for so long, and after so many cell cycles, that normal cell will then become a cancerous cell.
Fascinating.
Yep.
Terrifying, but fascinating.
Yeah.
One quick question before we go to a question and answer. So you said the latency period. Can it go back into latency once it's come out of latency?
Yes, so the virus can reactivate, it's called, and so enter a lytic cycle. So this is when you will have symptoms, so you can have cold sores and things like this. And this is when the virus senses that there is some kind of stress. And so the virus senses that the host is all of a sudden stressed out. And so that's why we see in college-age students that they get cold sores when they have exams. Because there's a lot of stress in them, a lot of hormones coming up, and so all of a sudden you get those cold sores, and that's the virus sensing, oh my gosh, my host is going to die, so I need to get out. And so they can enter this lytic phase, but they can also go back to latency and go dormant again, and you won't hear about them for a long time after that.
Awesome, thank you so much. All right, we are going to open it up for our first question and answer. Feel free to raise your hand. We are also going to be taking Zoom questions. I'm just for Zoom people, you can either raise your hand or we will read out the question or have you read out the question, or you can answer it, submit it through the question and answer button. So either way with that. Sorry, that was a little muddled at the end there. All right, does anybody have any questions? Somebody in the back.
Yeah, so I'm interested in, are the people out there who don't have herpes virus? What about babies when they're born?
Okay.
They have herpes. Are they transmitted through like sex cells and stuff?
Awesome. So we have a question of, essentially, is there anyone without herpes, for example, babies, or anyone out there, really? Was there a follow-up to that? I'm sorry if I just cut you off.
No, that's great.
Okay.
All right, so all of us here have some kind of herpes. It may not be the herpes you're thinking about, the one that you're ashamed of, you should not be, but that's just the way it is. But we all have some kind of herpes. So if you had chickenpox as a kid, that's a herpes virus. If you had mono, that's a herpes virus. So you most likely we all have at least one. Babies, they're not necessarily born with herpes. They can get it when they go through birth. But most of the time they're not. And so actually herpes, even herpes simplex, is actually pretty bad for babies. It can cause encephalitis. And so if you have cold sores, do not approach a baby because they will get infected and it can be very bad for them.
And just a little jargon
Yes,
check.
yeah.
What is encephalitis?
It is your brain going way too high in temperature, and that can lead to death. So you don't want this.
Awesome. Thank you. Any other questions? Yes.
Does a shingles vaccine get rid of a latent chickenpox?
So the question is, does a shingles vaccine get rid of a latent chickenpox?
Yeah, so that's an interesting question. So you are at risk of shingles if you had chickenpox. And the reason for that is that your chickenpox is your primary infection with one type of herpes. It's called BCV. And so you will get chickenpox, that's your primary infection, and then the virus will go latent for years and years and years. And so later on in your life, you will get shingle from that same initial infection. And so the shingle vaccine is going after viruses that are in their latent phase. So yes, you would get rid of those. You would basically force reactivation of the virus so that the immune system can get rid of most of those viruses.
Anybody else? I think we can take one more. Yeah.
We have one from Zoom. They've raised their hands, so I can allow them to talk. All right. Elaine, you can speak now, I believe, if you want to. Oh, but I can't hear you.
Are you muted?
That's a great question. We're going to try to put it on a different speaker.
Have patience with us, folks.
I'm
This is a
sorry.
new world of hybrid.
Elaine, could you try speaking again? Volume's at 100%. It's not working.
Okay. Elaine, we are going to have you type in your question, I'm afraid. I think we're going to go to that right now until we can figure out what that technical issue is. But we can take that in the next question and answer, and we'll move on to the next questions.
I think they typed it.
Okay, we can take it real quick.
Are there any beneficial to human herpes viruses or other latent viruses?
Awesome. So the question is there any beneficial to human herpes viruses? Or what was the second part, latent?
Or other latent viruses?
Or other latent viruses?
I don't think so. Viruses are not, in it for you. They're in it for themselves. So there's really no benefit. I don't think so. That's a great question. I will look into that.
Awesome. Thank you. All right. So we're going to go a little bit to what your lab specific focus is. So we've talked about different types of herpes viruses and stuff like that, but I know you guys look at some particular ones. And we've mentioned onco herpes viruses. But I think there's some specific ones that you guys are particularly interested in.
Yeah, so we study, in the world of herpes viruses, we study one that's called KSHV. It's called Kaposi sarcoma-associated herpes virus. Kaposi sarcoma, you may have heard of it. It was the sort of the defining disease in the 80s for HIV positive patients. And there was a lot of stigma around it because it's a cancer of your skin that gives you kind of large red blisters on your skin. And so this was something that had a lot of stigma attached to it because it was very visible and it was in HIV positive patients. And so this cancer, turns out, is caused by a herpes virus. A herpes virus that many of us carry, but we don't hear about this virus. This one in particular does not give us any symptom unless we become immunocompromised. And so it is a big problem with people who are carrying HIV and in people that have organ transplant, for example, because they are on immunosuppressors. And so really when this sort of new type of cancer completely exploded in the 80s, people went after the cause of it, and so this is when we found this KSHV virus that we are now studying.
Intriguing. So the actual virus itself, what is special about it? Why this virus? Why is this the herpes virus for you?
Why is it the one? It's a very interesting virus. Like all herpes viruses, they're very interesting, but this one has a little particularity is that this virus will have a specific strategy to co-opt sort of the resources of the host. And so, like all herpes viruses, it will go into a latent phase for many, many years, but at some point it will reactivate. And during this reactivation phase, there's a lot going on. The virus goes from really doing nothing in your cells to basically doing everything. All of a sudden, this virus has to express all of its viral proteins, replicate its DNA genome, and these are kind of big viruses, so there's a lot to do during reactivation. And so, obviously, when in the latent form, your immune system doesn't have any clue that the cell is infected. During lytic reactivation, the immune system is very aware of what's going on because there's a lot of viral activity. And so to do this, to be able to, use all those resources without having the immune system kick in, the virus is doing something very specific that we study, and that is targeting RNA, we talked about RNA, for degradation.
Interesting. Okay. So how does this virus actually infect humans? So it's not necessarily causing any symptoms in people that aren't immunosuppressed or immunocompromised. So are only the immunocompromised spreading it, or can you get it from a non-symptomatic person?
No, so you won't be aware that the virus is entering this lytic cycle and producing new viral particles, but you will carry them in your saliva. And so this is sort of like EBV, you transmit it by saliva. KSHV is sort of the same. And so you will not know you're infected. You will not know that you're giving it away to the person with who you're sharing saliva. And that's just how it's spread out throughout the population.
I'm going to do another jargon check. What's EBV? Or EBV?
EBV is Epstein-Barr virus. This is another herpes virus that's causing, most people know about it because of mono. Mono is caused by a type of herpes.
Awesome, thank you very much. So how does KSHV interact with the host cells? Is it the same way? Is there something special about it, or is it that standard kind of herpes cycle that you talked about a little bit before?
Yeah, it's pretty standard for herpes virus. So again, this alternative latency and lytic cycle, and then really in this lytic cycle, the specificity of KSHV is that RNA degradation event that not all herpes viruses are doing. So
What happens in that? Like, what is so important about that? What makes that so difficult?
Yeah, so there's this imperative for viruses to find a way to express their protein. That's the one thing that viruses don't know how to do, is to make protein. That seems pretty basic compared to everything else that they can do, but they still haven't figured this out. So they don't know how to make proteins. So to make proteins, they have to use our machinery. We know very well how to make proteins, and so they have to use our machinery. And how do you make proteins? You force feed RNA into a protein translation machinery. So you have RNA, and viruses know how to make RNA. We have RNA. And so to make proteins, you take that RNA and you force feed it to the protein machinery. And so all viruses have to find a way to get into that protein factory, and they have to find a way to make proteins. And so they all do it differently. And we can talk about that with other viruses, but the way that our virus do it, or KSHV is doing it, is by degrading the RNA of the host so that there's no more RNA coming from the host, from the human cell, and instead all the viral RNA are now free to use this translation, this protein factory for themselves. And so we're trying to understand this.
I don't know, it sounds like they figured out the perfect system to make proteins. They don't have to worry about it.
Yeah,
They've got
pretty
somebody
good
else
at
to
it.
do it.
Yeah.
Ideal. All right, so what are some of these symptoms? Is it just that kind of sore? Is there, because that doesn't usually, like, is that going to kill us? Like, what's the other symptoms that are really causing the harm, I guess, is the question.
Yeah, so for most people, again, if you're immunocompetent, like we say, then you would not have any symptoms, really. You're not aware that you're infected. It's when you're immunocompromised that really, whenever that virus is reactivating, there's a lot going on, and the immune system is not picking up on it, and they infect a very specific type of cells. They infect B cells, which themselves are immune cells, so it's kind of HIV, it's sort of the perfect world for a virus. And so what will drive those cancers, those B-cell lymphomas and Kaposi sarcoma, is that they will drive overproduction of these cells, and so these cells will divide, and this is the typical story of cancer where you have no control over those dividing cells, and so you end up with tumors or lesions that are cancerous, and that will eventually lead to death, yes.
Awesome, okay. Well, not awesome, but interesting. All right, so you focused on the mRNA that doesn't get degraded. So the mRNA that's able to escape, is that the right way to say it, I guess? KSHV. What's that important about that?
All right, well, like I said, what the virus figured out is how to put its own RNA into the protein factory. That's great for the virus, it's making its own viral proteins. So to do this, it has to remove the host, the human RNA, so that it can get into the protein factory. But the host cell, us, the host, we're not happy about that. This is kind of a big deal in the cell to co-opt this protein factory. And so the host cell is not happy about that at all. And so the host is fighting back. It's doing its best to regain control, stop this viral takeover. And so what we detect in our lab is that there are some RNA that should be degraded because the virus is targeting them, the virus should degrade them, but they're not degraded. And so there's something about them that is very resistant to this viral invader, and there's something about them that is here to protect our cells. And so this is what we're trying to understand. And if we can understand this, how is it that those RNA are escaping? Then we could block the virus from doing this, from getting into this protein factory. If you block the access to the protein factory, you block infection, you will destroy this virus. And so this is why we do this.
Awesome. So RNA becomes proteins. That's like what they are turned into. That's not quite the right term, but that's what they become eventually. So what kind of things does this RNA make that survives? Do we know? Is it something like crucial, or does it just seem to be random pieces of RNA that should have been destroyed?
So it's certainly not random. So we can go in and tweak different things, and we always find the same RNA that are escaping degradation. But what they do is kind of all over the map. And so when we got into this project, we were sure that we would find, component of the immune system, maybe something that really is antiviral or something like this. And some of them are, but some of them have nothing to do with anything that we were suspecting. And so this is really surprising. And this is also why I do science, is like, you go in like, oh, I'm sure this is gonna work out this way. And it turns out it has nothing to do with what you were thinking of. And so that's also kind of fun to study and go after that.
For sure. So I'm going to do a little bit of a wrap up before we do another question and answer session. So what's the biggest takeaway you've had for your research so far? Like, if there's one thing you want people to remember, like, hey, yeah, I'm putting you on the spot. I'm sorry. What's the big ticket item that you think is important for people to know? It can be anything.
Yeah, well, I think, and again, the last 2 years in this pandemic has really hurt us a lot, but I want people to still remember the beauty in viruses. They are really, sorry, I know it's rough to say this after this pandemic, but they're really smart. They're really tiny, and they're really smart. The example that I give my students all the time is Ebola, for example. When you hear about Ebola, it's such a scary virus. It's doing so much hurt. It has only 4 proteins. It's so tiny, and it's doing a lot. And so I think we have a lot to learn about these viruses, and this is really the beauty that I see in them.
They're really minimalistic but powerful little buggers down there.
Right.
Man. All right. So we're going to open up to another question and answer session. For those of you on Zoom, if you could just type your answers. I'm sorry, we don't 100% have the speaking version good, but just do the typed questions right now. And anyone in our audience, you guys are free to just ask your questions normally. Yes?
I've heard that there's a number of herpes trials that have taken place in different parts of the world. Did any of them show any promise at all?
So the question is that there are a number of different herpes trials taking place across the world. And are there any positive kind of outputs from them? Anything that we want to know about?
Yeah, so there's a lot of vaccine trials going on for herpes, and not for HSV1 or HSV2, the ones that are giving you the cold sores, because we really don't care about those. We are going after those herpes viruses that are causing cancer, and we are discovering that those herpes viruses are also doing a lot of harms. And so you probably have heard of CMV, which is a herpes virus that causes a lot of birth defects. Recently, EBV, the same virus I was telling you about that's causing mono, has been associated with MS, multiple sclerosis. And so there's a big drive to try and get rid of those viruses. The trials are actually pretty promising. They're working great. The only problem is that you need to get people vaccinated before they get infected. And so these would be the type of vaccine that you would need to get within your first 6 months. And so for the rest of us who are already infected, we would have to think of something else.
Any other questions for this section? Yeah, go ahead.
I'm just curious, what makes something a herpes virus? Is there a specific genetic similarity, or is it just the fact that they are latent and they come back?
Awesome. So the question is, what makes a herpes virus? Is there a certain set of qualifications, sort of, or is it just the fact that they are latent and then come back?
Yeah, so the herpes virus family, their genome is actually quite similar to one another. They have some specificity, some proteins are expressed here and there and all of this, but they are, their tree, their phylogenetic tree is very different than any other viruses. And so this is really how you separate different viruses. And so in the world of DNA viruses, let's not even consider RNA viruses, they are certainly very different than the other ones. They're much bigger and they have a certain set of proteins. But the fact that they go latent or lytic, this is something that other viruses can do that are completely unrelated. So typically phages that infect bacteria. They also do the same cycles of latency and lytic, but they're so different than herpes viruses.
And is phages just short for bacteriophages? So the bacteria is the viruses that affect bacteria?
Yeah. Another beautiful thing about viruses, they can infect bacteria. They can do everything, really. Enjoy my life.
Any other questions? Anything from Zoom? All right, we will move on to the next session. So, a couple of different questions in this section. So first, you are currently working on figuring out what's different between these mRNAs. That's your current goal? Is that like your big overarching where you're going? That's your next project right now?
Yeah, so we want to go after this. We want to understand why is it that some RNA are degraded and some RNA are not. And especially now in this sort of new world, new post-COVID world where there's a lot of money going into RNA drugs, we think that if we can understand really what's at the core of this difference, then we can make a drug that could block a lytic infection. So this is really something that we're interested in. I'm telling you this like I will have the answer in like 6 months. No, talk to me in 20 years. I probably won't know much more about this, but we're going after this.
Nice, I'm glad you are. So how has the pandemic affected your fields? Because I know you mentioned it a couple times and we've all mentioned it plenty of times over the weeks, months, years that it's been going on. But how has this changed your field overall, how you think about viruses, anything along those lines?
A lot has changed in every possible ways. So first, it's this relationships to the public. A lot more people are interested in viruses, and this is awesome. And at the beginning of the pandemic, I kept receiving emails and questions from all kinds of people really trying to understand how viruses work. And this felt, kind of good, like feeling like I was useful explaining to people, how these things work and, what we can expect and all of this. And then as the months passed, there was a lot of misinformation, a lot of mistrust between scientists and the public. And so it sort of shifted, and now it's kind of the opposite, where people are kind of worried about what virologists are doing, questioning whether we know what we're doing and if we're safe enough and if all of this is worth it and why are we being paid to do this type of research. And so it went from being very uplifting, finally I'm doing something good, to being kind of like, now if I sit next to someone on an airplane, like I won't tell them I'm a virologist. I will tell them I work on cancer, and that's something we can talk about, but I don't want to talk about viruses anymore with people. So that changed a lot. It changed a lot also the way that funding works for a lab. So obviously to do all this research, we need a lot of money, and so a part of my job, a big part of my job is going around sort of begging for money from all kinds of, foundation and the government and, anyone that can give us significant money to do this research. And so as the pandemic was hitting, there was also a lot of frustration because all the coronavirus experts didn't have any money because the government didn't think this was important until it hit. And then all of a sudden they had all the money. So then everyone else was frustrated. That, wasn't fun. And then it changed a lot, sort of everyone's spirits. I kind of want to say that everyone is a bit burnt out right now. We're all very tired. We want things to move on, but at the same time we know it's not moving on, and our life is going to be different from now on, and we know it, and it's kind of hard to accept. So I will say that like every aspect of my daily life is different now.
Yeah, I feel that a lot. In a different way, but I feel that a lot. So you did do some new things though, I think, during the pandemic. You did do some radio show talks and stuff like that to get information out there. And I think if you, like, the importance of science communication in these sorts of times, because you touched on a little bit of the misinformation and how important it is to get this sort of understandable work out there. Can you talk a little bit about your experience with that?
Yeah, it's always something that I think about, like, if you don't have the proper scientific background, how are you going to understand anything? And there was a lot of kind of looking down on people not wanting to get vaccinated, but at the same time, this vaccine came out really quickly, and so if you don't understand what's behind it, I understand that you would be a little scared of, getting a vaccine for something you don't necessarily understand. And so it is so important to have people do the work and actually talk to people, trying to explain how things work, so that there's a real trust between scientists and the public, and so that we can move forward with these things without being confrontational with people and not trying to force them to do things, not trying to not explain to them why, at the beginning people were saying, oh, any kind of mask is fine, and then 6 months later it was like, stop this with your bad math. You know, it's we learn and we move forward, and so it's so important to be honest, and it's still very hard to do. And I have a lot of friends, coronavirus expert, who've been doing a lot of public outreach, and now they're receiving death threats for all their good work. And so I understand that people don't want to do this, but it is so important.
Yes, thank you for coming to
I mean,
do
not
this. So one of the things that I do want to switch gears a little bit, because I want to make sure that we do focus on this, is you do a lot of artwork as well. So you have, our poster this week is one of your pieces. I think the beginner slide that we had was also one of your pieces. Do you want to share a little bit more? I think you have a slide or two.
Yeah, so this is a little selection of the things that I drew. As you will see, it's busy. It's kind of always the same thing of very busy drawing, basically. And that's just because I always have to do something with my hands. I don't know what it is. Maybe I should be diagnosed with something. Who knows? It's never too late. And so basically for me, art and drawing, and I do all kinds of things. Like I have an image of an earring on there. That's because I made it in my lab. I have, quilling on the right. And it's just because I need to do something with my hands all the time. And so, science is good for this, because when you're in a lab and you're at the bench, like there's always something to do, there's always stuff to make, and there's always things to look at. But now I'm not doing experiments anymore. Now my students are doing all the experiments for me, which is awesome. But at the same time, it's like, what do I do now? And so when I have things in my head, or when I have to take a moment for myself, drawing and painting and all of this is really something that I enjoy doing.
Awesome. Do you have a particular method for deciding what type of art you're going to do, or is it just what hits you?
Yeah, it gets stuck in my head. So like I would wake up in the middle of the night thinking of something, and then I think about it for 2 weeks, and I'm like, I need to get this out of my head, and I buy stuff to do it, whatever it might be, and then I do it, and then I never touch it again. Ask my husband, like, we have plenty of stuff at home if you want to do all of this.
Awesome. I like it though. So this is something that I think even within like the science community, people debate back and forth. So oftentimes people say it's STEM or art, and they're like two opposing sides. But in different experiences, even I know within Science Cafe, we were talking about it ourselves, of like different people have had the like more of the STEAM conversation, science, technology, engineering, art, and math. And that sort of conversation. Do you feel like that's a dichotomy, or do you feel like it's a very close relationship?
I think it will depend on each person you ask that. I know for me it helps me in my downtime to stay busy and sort of quiet down my brain. And I know a lot of people feel that way, and if you talk to scientists, you'll see that they are often people that are very creative and are really into their head a lot, and so having a way to express this is very important, and it can take many forms. And so it could be art, and it could be people singing and dancing and doing yoga, or just laying on the grass after a long hike. It takes many shapes, but people need that.
During my undergrad tour, when I was deciding where to go, I've never seen so many a cappella groups in all of the different STEM schools that I went to tour. Oh my God, every single one had them. It was amazing.
Yeah.
I joined one too. But yes, I am of the, it depends on the person, but it definitely is a relationship.
Yeah.
All right, so I do want to talk a little bit about your Cell Press Journal Trends Voices article that you did. So this is a way of amplifying voices and inclusion and diversity, and you did a piece, you were featured in it, you had a piece in there. And I know I have a little blurb from them because I think it was important that we wanted to talk about them a little bit, and so we'll share this in our post because we have a follow-up post as well, because we think these guys are pretty cool. They hope that scientists share their personal stories and ways of redressing existing bias in scientific inquiry for the benefit of science and society, and I think that's a really cool way to think about it. So you received this highlight because you're a first generation student. What was your journey as a scientist like? And do you want to tell us a little bit more? I know you had a lot of your education in France and that sort of stuff, so it's a bit of a different world than maybe what we're experiencing over here sometimes.
Yeah, so this is something that has been evolving a lot inside of me. Growing up, we didn't have much. So I'm first gen, as in my parents never even stepped foot into a high school. And so, growing up, this is not something that I was talking to people about. Growing up in the south of France, like I had a very strong French accent, and I kind of on purpose try to lose it over time so that people would not notice that I came from the south. And then going to school, even though education is free in France, so that certainly helped me. You still don't know where you're going. You want to go to the university? Sure, let's pick a major. What do you want to do? What kind of job do you have after that? You don't know. You only know the things that you see. And so, I started thinking, oh, I could be a teacher. These are sort of the fanciest people I see around me are my teachers. They're so knowledgeable, they know a lot, they do good work. Maybe this is what I will do. And so I started this way, kind of randomly studying biology and geology. Kind of embarrassed about that, but whatever.
It's awesome, you don't have to.
Oh God. And so I loved it. And so as I was progressing, I was seeing more people, and then I was seeing people doing science, and I was like, oh, maybe I can do some type of science, maybe be a lab tech or something like this. And so I continued that way, kind of randomly again, and until I ended up, in a PhD lab. And I was like, okay, well, I guess this is it. This is where I belong in the end. I like it. This is very stimulating for my messed up brain. And I like it. This is what I wanted to do with my life. And so, it's hard because you don't know where to go. So you count on people to sort of help you and tell you how you can get to where you want to go if you don't have that family support around you. And then, it's just a story of randomness and good luck, I guess. And so, again, like being a first gen, this is not something I was telling people in the past because I was sort of embarrassed about this, but now I tell everyone I see because I think like people should know that you can make it. You can get to where we are right now, even if you start from the very bottom of that barrel, that very sad barrel. And you can really do whatever you want if your heart is in it. And so now I tell everyone, and I'm happy to tell them that, I can buy clothes when I was a kid, I was given clothes, and, all these things like that I used to be embarrassed about, but that actually are a big strength in my lifetime.
Thanks, I like that. That's a great way to look at it. I really like that, sharing that sort of part of you. So one thing that changes a lot, I think, coming into academia from having like no perspective from the outside, because I think at least in some ways I was similar, like there weren't any PhD students around me, like I didn't grow up with that. So like, what is the view of academia from the outside versus the inside once you were kind of in it? How has that changed?
Well, it changed a lot because I didn't know it existed. Like, I didn't know scientist was a real job. Like, maybe you see someone on TV, like, they're fighting crimes and they go back to the lab and do this one experiment in like half a second and you're like, oh, that's kind of cool. And then you get to a lab, it's not like this at all. But like, so like it changed a lot in the sense that I didn't know this whole word existed. Like, what's a professor? Like, what are we doing every day? Who's paying us? All of this I didn't know about. So from the inside now, I try to explain to people what I do. But for example, for my family, so I'm an assistant professor, that's my official title, and when I tell my family that I'm assistant professor, they're like, who are you assisting? Like, you've been in school for 20 years, who are you assisting? So it's hard to make this connection.
Yeah, I feel that. And so, how do you approach mentorship in science? Because I feel like this is important as well, and both in like mentoring any student, but also using your experience to mentor students.
Yeah, mentoring is really hard. Plenty of a student in this room, so mentoring is hard because nothing prepares you for it. So you spend your entire training getting all the skills that you need for your experiments and being the best at what you do and really going after the best science. And then you get your job at a university and you have to manage a lab. All of a sudden, you have to figure out what to do with your money, who to hire, how to mentor them, and no one prepares you for this. It's like you're thrown into this, and good luck. We'll see you in 5 years. See if we, renew your contract. And so at first I was like, all right, great. Everyone will be like me, A-type personality, super enthusiastic about everything, really hardworking and everything. And it turns out, surprise, surprise, everyone's different. Like, who knew? And so like I had this very set way of thinking of things, like we're gonna meet this day at this hour, we're gonna talk about this, and we'll do this my way, and it doesn't work. If you do this your way, it doesn't work. So you kind of have to figure out real quick that you have to adapt to everyone. Everyone's different in their needs. Everyone is different in their needs for independence, for hand-holding, for supervision, or all of this, and so you have to adapt. And so you become a mentor by being in contact with your mentee. I have been extremely fortunate. Everyone in my lab has been really awesome, and so they made my life really easy by being the best people, really. But I can see how this could be very difficult, and we'll see what the future brings. But as of right now, I think we're doing really good.
I'm glad. Good. So one final question, and we don't always get the opportunity to kind of ask these sorts of things just because we don't always have people who've had different kind of educational backgrounds from not the US and that sort of stuff. So what does you've been in our education system from the other side, obviously, and also in your postdoc. So like, contrast, I guess, compare and contrast. What does our education system have to offer that's really good? And also, what are some things we can improve? Because we know we can improve.
Yeah, so obviously from my perspective, the first thing that needs to be improved is the cost of education. Like, you cannot be inclusive in higher education when you ask students to pay so much. This is not inclusive, people, and we can talk about inclusivity all we want, but until we fix that, it's not gonna happen. So that's the main thing. But I will say that the major difference in the other direction that I think we're not doing very well in France is that it's very old school, and so you have to figure it out. You're in there, you're thrown into higher education, and you just have to make it, and that's the way it is. I feel here students have more contact with their professors, and they have people advising them on different things, like career advice and all of this, and they make more well-rounded people. And I think people here are way more adjusted than what they are in France, and they think about things that are bigger than themselves, and they really inspire me, and they're very uplifting in the way that they think about the world and pushing all of this forward, and again thinking about inclusivity and diversity and all of these things that in France it's just like people don't think about it. It doesn't exist. We're not taking stats about any of this, and so it doesn't exist. Basically, that's what they say. And so there's a lot that we have to learn in France from the way things are run here in the U.S. But my biggest grief is always tuition. Yeah.
It's been a grief for a lot of us, I have to say.
Yeah.
Man, oh man. So I'm going to open it up to the crowd for the last bit of question and answers. We are going to have some time at the end. If you have any straggler ones, feel free to get more pizza, have a conversation and stuff like that. But do we have any questions that we want to answer now, ask now, rather? It's okay if no. Just gonna give the awkward pause when I'm teaching in front of the class.
Yeah.
All right, we're gonna call it there then. All right, everyone, so I am just going to do a little outro down at the end, just for information about our next cafe and stuff like that. So thank you, everyone, first of all. Look out for emails for our next event with Dr. Ana Castedo on weedy plant evolution. Very exciting. So yes, weeds, but also the importance of them, what they do, agriculture, very exciting. It is going to be posted in Spanish with live English interpretation, so if you don't speak Spanish, it's okay. There will be audio English translation. The location is not going to be at Amherst Women's Club. We are doing some new things and moving around a little bit, so this one is going to be in Springfield, but we are also going to have the Zoom option as well if you can't make it out there. You will see in the emails, it's going to be at the Hispanic American Library. It's a really beautiful location. We're really looking forward to doing it there. If you don't currently get our emails, feel free to sign up on the sign-in sheet, or also we're going to send out a virtual sign-in sheet for those of you on Zoom. And if you want to have any more information about us, I actually should also, oh yeah, we already did it. Thank you, Janelle. You can find us at our website at oebsciencecafe.org, or also on any of our socials if you want to follow us there. It's a good place to figure out what we're doing. So thank you very much, everyone. Thank you for joining us, and thank you for a great conversation today. And we're signing off here.